Hello and welcome back to part two of today's stream. We just finished day 7. I guess because this is going up on YouTube, I say I'm Jared. You can call me Jardo. We just finished day 7 of the Advent of Code 2024, and we are moving into day 8. Day 7 was just searching through a tree for some results. Didn't turn into anything too crazy. Just some pretty normal looking Advent of Code solution code. The only real thing that we tried out was we made our own enumerable object by including enumerable and implementing each for iterating through the possible solutions. But we didn't actually do it in a lazy way because it turned out we didn't need to. The part 2 was kind of slow, but didn't really matter. So let's get into day 8 here. You find yourself on the roof of a top-secret Easter Bunny installation. While the historians do their thing, you take a look at the familiar huge antenna. Much to your surprise, it seems to have been reconfigured to emit a signal that makes people 0.1% more likely to buy Easter Bunny brand imitation mediocre chocolate as a Christmas gift. Unthinkable. Scanning across the city, you find that there are actually many such antennas. Each antenna is tuned to a specific frequency indicated by a single lowercase letter, uppercase letter, or digit. You create a map, your puzzle input, of these inputs. For example, and I guess let's just take a glance at our input while we're here. Okay, that's a relatively small input. And so here's our example one. So what did they say? It's letter, lowercase letter, uppercase letter, or digit. The signal only applies its nefarious effect at specific antinodes based on the resonant frequencies of the antennas. In particular, an antinode occurs at any point that is perfectly in line with two antennas of the same frequency, but only when one of the antennas is twice as far away as the other. Okay, let me read through that again. The signal only applies its nefarious effect at specific antinodes based on the resonant frequencies of the antennas. In particular, the antinode occurs at any point that is perfectly in line with two antennas of the same frequency, but only when one of the antennas is twice as far away as the other. This means that for any pair of antennas with the same frequency, there are two antinodes, one on either side of them. So, okay. Couldn't there be an antinode between them? Because if they're like 4 apart, there's an A here. Isn't this a point that's twice as far from this one as from this one? And so is this. Anyway, we'll continue on. So for these two antennae with the frequency A, they create the two antinodes marked with a hash. Okay. Adding a third antenna with the same frequency creates several more antinodes. It would ideally add 4 antinodes, but 2 are off the right side of the map, so instead it adds only 2. Okay. Sure, maybe there's a product of the input that this doesn't happen. I have to think about that. Antennas with different frequencies don't create antinodes. A and A count is different. Capital A and lowercase a count is different frequencies. However, antennas can occur at locations that contain antennas. In this diagram, the lone antenna with frequency capital A creates no antinodes, but has a lowercase a frequency antinode at its location. The first example has antennas with 2 different frequencies, so the antinodes look like this, plus an antenna node overlapping the topmost A frequency antenna. Because the topmost A frequency antenna overlaps with a 0 frequency antenna node, there are 14 total unique locations that contain an antinode within the bounds of the map. Calculate the impact of the signal. How many locations within the bounds of the map contain an antinode? Interesting. Okay. So there's our map. We can just taking a look at it to think about things, so we can easily highlight. How do I toggle case sensitive? How do we do the math to figure out where these things are? Surely if we have the delta between the two of them, that's something we can figure out, right? So I'm thinking like, oh, we know we have one here and here. Let's say, for an example, let's say we know we have one at 1, 5, and 6, 2. I don't know. That's arbitrary. Which means the delta is 5 minus 3. Or minus 5, 3, whatever you want to, either way. How do we figure out oh, it's just again as far in each direction, right? Yeah. Let's confirm that with our inputs. So yeah, it's just again as far in any given direction. And we have to hit up all the combinations. Okay. So I think one of the first things we'll do is let's implement a point class. This is just going to be a data class that has an X and a Y. It might not even have any other methods. And for the sake of brevity, we're going to call it P. And we're going to do a little read lines, jump true. And then we need to store everything in a something. Store all these points in a, do it in a hash. So we'll store the antinodes in a set because we want to make sure that we're just counting unique ones. But as we create this hash, so this is antennas. It's hash, and we'll set the keys to be the points and the values to be the. Actually, let's set the keys to be the frequencies, and the values to be an array of the points where there is an antenna for that frequency. That makes more sense. So we're just going to define a new hash whose default values are new arrays. Interesting. All right. So then we can iterate over our input, each with index. Will get us a new line. Man, that pipe bug is really frustrating. And that is the y index, and then line.chars each with index will give us the character and the x coordinate, and then we'll say next if the character is another period. Otherwise, we want to antennas. So we said char here. Let's say frequency. Let's use the domain words here. Frequency, and we will shovel in the current point, which will be xy. Excuse me. Sorry, I don't have a quick easy mute button. I have to set that up. That should give us a big hash. Undefined local variable x. Okay, so that I forgot to put, these are symbols, not local variables. I forgot to rename that. And now we have antennas. Perfect. We should also figure out what the bounds are. So I'm gonna say, this thing's probably square though, right? So I'm just gonna say size equals nil, because I'm gonna need access to this later. And when we hit our first line, I'm gonna say line.length, or size or equals line.length, so that we just save that value for later. And then we can create bounds out of it. Specifically, we can just say bounds. Actually, we don't even need the size. We just need the bounds. We can do that here. And then, so once we have that, I guess we need to iterate over each frequency. So this is where we create our anti-nodes set. And sorry, I haven't felt very inspired to write anything really weird today. We did all that operator overloading and other stuff in previous days, and just don't have ideas today. But neither do you, chat. You have been dead silent today. Well, so we just need to iterate over our antennas. Antennas will be frequency, but we don't actually use the frequency. And I mean, it's antennas with this frequency. I don't care. I'll just shadow it. Doesn't matter. And we want to look at the combinations. The two element combinations. Two element combinations. So I feel like we're adding the delta to one and subtracting to the other, and I don't remember which one it is. I have trouble visualizing, or I have aphantasia, so I have a total inability to visualize. So I have to kind of like reason those things out. All right. But each one could have two. And for each of them, once we figure out what they are, which we've not done yet, if antinode or if bounds.cover antinode, then we want to shovel it into our antinodes, which takes care of duplication because it's a set and not an array. And this is not syntactically valid because of something. Something not obvious to me. Why is this not? Oh, I see it. We were missing an end. There we go. And so that's just a matter of figuring what those two antinodes are. And are we just subtracting one from the other? No, it's the delta. So we need the delta. So we can, now I know Ruby has vectors in the standard library, but we're not going to use them. So we're brave. Oh, let's just fix that for now. We're going to do this ourselves because it's fun. It's more fun than just using what's in the standard library. So this is going to return a new data object with x minus other.x, y minus other.y. So then we can say the delta equals P1 minus P2, and we then, our antinodes, I think, are P1 minus delta and P2 plus delta. That could be wrong, but you know what? Feels right. And then the answer is antinodes.length. failed because undefined method combinations for instance of array. I think it's because it's called combination, which I don't agree with, but all right. And that fails because bounds.cover antinode is wrong. This is, we need to check because antinode is not like an integer. We need to check that both of the sides are covered. That gives us 213, which is, I don't know, a reasonable sounding number. Not the right answer. Too low. Interesting. Too low. Make sure we understood the problem, because we can use this test input. We may do that. Make sure we're doing the right thing. What was your approach? Well, currently we record all of the positions of the antennas and what frequency they're at. Then we iterate over each set of frequencies, grabbing all the combinations of two different antenna, figure out where their respective antinodes are. I'm not 100% sure this is correct, but we'll debug this using the sample input rather than the full input. Check that they are within the map, and if they are, then we add them to our set, which handles deduplication for us, and then we list the length. Then we look at the length. So I think let's I think it looks obviously wrong, so let's just try their test input. Let's see what we get. We get a 7. The correct answer is 14. So that's much too low. We could make it print out the map. That's totally reasonable. Yeah, let's print out the map. There's a dog playing with a squeak toy in my the hallway of my building, and my dog has just woken up and noticed this. All right, let's print out our board here. I guess we can use our bounds as our iterator here. It doesn't matter whether, wait, no, it does matter. It does matter what order we iterate in, because we're printing out to a terminal. And let's just start. Do you have to, I don't think I have to specify anything. So that should print an empty map. And that's the same size. And we should be able to say, or actually we need to, so our data structure isn't particularly conducive to this, to doing this efficiently. I am going to antennas by position is antennas flat map. Frequency antennas. Doesn't matter that we're shadowing them here. And then this has got to return antennas.map. So just a point, and we return the frequency. No, the point, and then the frequency. And then we convert that to a hash, and then here we can say antennas by position, and then index it by the point, xy, or that. And that should get us the original result. And let's just compare that, make sure these are in fact the same. So we've got what? 1, 2, 3, that's 5, 6, 7, 8, 9, 10, 11, 12, 13. That seems too big. This is 5, this is 10. What? So we got too much. We appear to have done something wrong. Because our map is too big, and it's too big. This is probably supposed to be -1 at minimum. Five, 6, 7, 8, 9, 10, 11, 12. So that's 12, but this isn't 12. The top 0 should be 3. Oh no, this is. Oh, yeah, this is right. 5, 3. Yeah, okay, this is right. This is right. Okay, we're good now. This map was bigger than. I've got mixed up with these other examples. This big map. Okay. So now we can also handle the case where there is a antinode here. So we can show the antinodes on our map as well. And we just need to look this up similarly. Include that. That didn't change any result. That didn't change anything. Why is that not working? Why are we getting no antinodes? What am I missing? Jeez. it's not going to change anything. I was just testing that. Okay, so now we need to figure out why, for example, 5, 2, if x is 5 and y is 2. So this is telling me, from what I'm seeing, that that's going to be, that's found. Then why am I not getting any hashes in my output? What am I missing? And this in parens is also just going to be a hash, and that's still a hash. No, this is, as we can see from what I'm seeing in the debugger here, that exists already on the the object, so I don't need to do anything there. And I can even show. So like we can put a point into a hash here. So we have this hash where one of the keys is a point, and if I reassign that using a new instance of point with the same values, it works. So hashing has to be in place and working for this to, and set relies on the same mechanism in Ruby. It's believe we do. Yeah. Same thing, same hashing. So that's cool, but doesn't explain, like there's some kind of, I'm missing something dumb, because this is returning a hash in the situation we're expecting it to return a hash. So how would we still be getting a dot? What the heck's going on? I guess I can evaluate the whole thing and try and... Oh, that's interesting. Oh, is our bug causing us to have... Oh, we've done... Okay. That almost... I think that just tells me what the bug is. The bug is that these are backwards. Yeah, there we go. And we're getting the right result. Okay, perfect. And now we have the right result. Cool. All right, so let's just remove our debugging print statement. So just to explain, I was just kind of winging it when I wrote this code. We are supposed to be, if we're subtracting P2 from P1, then to get the delta, then we want to be adding, not subtracting the delta from P1. Otherwise, we are just getting the original value back. That seems obvious in retrospect, that subtracting something from something and then adding that back would get you the original result, or the opposite of what I just said. But subtracting something, no, I said the right thing, but I missed that. So let's just remove that, comment this out, and pop that in there. And now we have our part 1, or sorry, day 8, part 1. And let's continue to part 2. Watching over your shoulder as you work, one of the historians asks if you took the effects of resonant harmonics into your calculations. After updating your model, it turns out that an antinode occurs at any grid position exactly in line with two antennas of the same frequency, regardless of distance. This means that some of the new antinodes will occur at the position of each antenna, unless that antenna is the only one of its frequency. So these 3T antennas now create many antinodes. In fact, the 3T frequency antennas are all exactly in line with two antennas, so they are all also antinodes. This brings the total number of antinodes in the above example to 9. The original example now has 34 antinodes, including antinodes that appear on every antenna. Okay. We can do that. We can even just calculate it afterwards because we're only adding here. So we can even just move back to the original. So let's uncomment this because it'll be useful. Let's go back to the original. We're expecting to get 34. And we can just do more stuff. We can just do it again. So now the antinodes logic is going to be a bit different. So for starters, we can just place antinodes at P1 and P2. Though I think my algorithm is going to naturally place them at P2 anyway. Or at one of them anyway. But whatever, doesn't matter. I don't think it's going to significantly hurt our performance. So we can just step in a given direction until we go out of bounds. We can keep doing this. In fact, we can even, no, that doesn't work. So we'll do it as two separate loops. So we create this delta, and then we'll need to do this version and this version. So say antinode equals P1 plus delta until not bounds cover was an annoying check. But we'll just copy it here. And we'll actually, let's just apply this. Let's remember our combinatorics from university, and remember that we can change if it's not in brackets something and something, then it's equivalent to not something or not something else, which intuitively makes sense here, right? We're saying until either the bounds don't cover the x-axis or the bounds don't cover the y-axis. So we add our antinode to the antinodes, and then we do it again. But now we are adding to that antinode. So we're essentially that's neat. That's the standard RB auto simplifying, which you could actually make an argument that it shouldn't there. I don't really care. And then we can do this again in the other direction. Now we are subtracting. Let's see if that works. And I did that backwards. We are doing things backwards. Okay, and 34 is the right answer for the test input. So we may have our solution here. Cool, awesome. That was day 8. All right, so there wasn't much too crazy in here. I think the fun thing we did is that we used Ruby's new data classes that are new in Ruby 3.2, I believe, and we implemented we created value objects using them to define points. Now, yes, I know there are vectors in the standard library, but this is just sort of a good example of what you can do here, defining the operators to make the custom operators do what you would want them to do in these different situations. And then we did have a little bit of debugging fun there, printing out the map as expected. Was kind of funny because I failed to realize that the reason the map didn't look as expected wasn't a logic issue in my printing code, but was the logic issue in my actual solution, resulting in the map looking like it did. But that's it for now. Thanks for everyone for coming out to the stream. I'll probably be streaming, I would guess, tomorrow afternoon, probably 2:30 Pacific, something like that. I haven't looked at my schedule, so follow me on Mastodon or Blue Sky if you want to keep up with that, or just on here, here being Twitch. But thanks for coming out.